Linear and homogeneous differential equations. How can we use this quality of differential equations to combine solutions? Today we are going to discuss what is a linear differential equation, what is a linear homogeneous differential equation, what is a linear operator, and how these solutions to differential equations can be combined. So, what are linear differential equations? They take the following form. So what we essentially have here on the left-hand side is y and its derivatives multiplied by some functions of x. And on the right-hand side, we have some function of x as well. Now y is the function we are solving for. So y here is the dependent variable and x is the independent variable in our differential equation. An example of such an equation would be the following, where we have x squared y plus x minus 5 multiplied by the derivative of y, and that is equal to e to the x. So in this case, a0, this function of x, is simply x squared, a1 of x is x minus 5, and the function on the right-hand side, b of x, is e to the power of x. We can rewrite this using the following form, using something called a linear differential operator, where we still have these functions of x, a0, a1, to a sub n, and next to each of them, we have either a multiplicative factor of 1 or a derivative of a certain order. What this allows us to do is to write a linear differential equation like this, where if L is our linear differential operator, we can rewrite this equation as Ly is equal to b of x. Next, we are going to look at a special case of linear differential equations. It is those equations that are also homogeneous. And we call such equations homogeneous simply when b of x is equal to 0. That is, when the right-hand side of that equation is equal to 0. So we have Ly is equal to 0. An example of this equation could be something like this. Now, the reason we are even discussing any of this is because linear operators have a bunch of very interesting and useful properties. So first of them is the multiplicative property, where if we take the linear operator and apply it to cy, where c is some constant, that will simply be equal to c times that linear operator applied to the function. For example, if our L is d over dx and we apply that to the function 5x squared, that will be the same as 5 times that operator d over dx applied to x squared, because 5 is a constant and we can bring that out front. There's also the additive property, where if we apply a linear operator to a sum of two functions, it is the same as adding those operators applied to those functions individually. So an example of this would be something like this, where our linear operator L is equal to x to the 5 times the second order derivative with respect to x. And suppose we apply that to x cubed plus x squared. Now what we can do in this case is simply apply this operator to x cubed and x squared individually and then add those results together. If we combine the multiplicative property and the additive property, we can derive the following, that if we apply a linear operator to a linear combination of two functions, that is going to be equal to the linear combination of those operators applied to those functions individually. An example of this would be linear operator L being x to the 4 times d over dx applied to 2x squared plus 3x. In that case, we can bring the 2 in front of the x to the 4 times d over dx and apply that operator to x squared, and in a similar fashion, we can bring out the 3 in front of x to the 4 times d over dx and apply that operator to x. The reason this is so useful is because of something called the principle of superposition, which allows us to combine solutions to linear, homogeneous differential equations. Suppose that y1 and y2 are solutions to Ly is equal to 0. Then c1y1 plus c2y2 is also a solution. That is, any linear combination of those two solutions is also a solution to that equation. Let's try and prove that. By saying that y1 and y2 are solutions, we mean that they satisfy the differential equation. That is, ly1 is equal to 0, and ly2 is also equal to 0. Now that's important to remember, because now we can try and plug in y is equal to c1y1 plus c2y2. If we have something like this, ly is equal to L applied to c1y1 plus c2y2, we can apply the properties of linear operators, and that is simply going to be equal to c1ly1 plus c2ly2. Now remember, we said that both ly1 and ly2 are 0, which means that this whole thing is equal to 0. Now if you compare the leftmost side, ly, and the rightmost side, which is 0, it shows us that this y also satisfies the equation, which means that this y is also a solution. Let's have a look at a particular example. Suppose we have an equation like this, which is a second-order differential equation. Imagine that through some process, we obtain two different solutions. Y is equal to e to the power of minus x, and y is equal to e to the power of minus 6x. Because this equation is linear and homogeneous, we can apply the principle of superposition to combine those two solutions. What we can say is that the linear combination of those two solutions is also a solution. And if you want, you can plug this into the equation to verify that it satisfies the equality. So to summarize, linear differential equations have the form ly is equal to b of x, where L is the linear differential operator, y is the dependent variable, or the function we are solving for, and b of x is some function of x. Linear homogeneous differential equations have the form ly is equal to 0, that is, b of x is equal to 0 in that case. For linear operators, we have the property that if we apply that operator to a linear combination of two functions, that is going to be equal to the linear combination of that operator being applied to those functions individually. Which means that for differential equations of the form ly is equal to 0, or linear homogeneous differential equations that have solutions y1 and y2, the linear combination of y1 and y2 will also be a solution.